Okay, guys, welcome to Chapter 3. This is Chapter 3, Section 1. We're going to start with. The title of Chapter 3 is Differentiation. So in this section, we're going to start actually doing calculus. Up till now, we've been taking a look at calculus ideas and calculus concepts, but now in this section, we're actually going to do calculus. All right, the title of section 3.1 is the derivative and the tangent line problem. So in this section, we're going to take a look at how to find the slope of a tangent line to a curve at a point, how to use the limit definition to find the derivative of a function, and then take a look at that idea that's going to relate something we did before, continuity, to this new idea of differentiability. So understanding that relationship. Right? So basically, calculus grew out of four major problems that some mathematicians in Europe were working on during the 17th century. So 1600s, back then, whale oil lamps and pen and quill paper, and these guys were sitting around worrying about these four problems. The tangent line problem, which is the one we're going to discuss down here. Velocity and acceleration, which is an application of mathematics to the real world. Maximum and minimum problems, which has a wide variety of applications. Just about any area that uses equations or math to model situations is going to care about finding maximums and or minimums in terms of real world applications. And the area problem. And the area problem is deceiving because it reads area. It actually is the area problem, but then application, area can actually be a whole bunch of different things. Okay? Now, every single one of these problems boils down to the notion of a limit in some way. And then calculus grew out of how that concept of a limit could be applied to the mechanics of the mathematics. All right, so we're going to start out by taking a look at calculus, the definition of our calculus, and differentiability through the tangent line problem. Okay. All right, so first off, let's define what it means for a line to be tangent to a curve. Right? So when we say that a line is tangent to a curve, what we're saying is there is a single point somewhere on that curve, and in all three of these graphs, we almost always call that point P. And there is a line that at that point P touches the curve, and the slope of the line at that point P is the same as the slope of the curve at that point P. Now, clearly, if you were to move that point P to somewhere else, then that tangent line would require a different slope for it to work. And if you were to put that point P somewhere else, you would need a new tangent line. So when we're talking about these tangent lines to curves, there is not a tangent line to a curve. There is a tangent line to a curve for every point on the curve. Now, some people get hung up with the idea of the tangent line only touching at one point because they look at pictures like this and they say, but what about over here? Yeah, it is true that the curve does intersect the tangent line, or the tangent line does intersect the curve, how you want to say that. But what we're concerned about, though, is we're concerned about that point of tangency right there. And that the equation of that tangent line is going to be determined not by this down here, but rather solely by that point there. Okay? A tangent line can also cross a curve, kind of like that one in the middle. Right? All right, so here's our problem, though. Right? This is what these early people who were working on calculus wanted to know. Is they wanted to know how to find the equation of this tangent line. That's an N right there. Right? So how do you find the equation of a line that is tangent to a curve? Right? Because our problem exists in that algebra taught us this. The slope of a line was y sub 2 minus y sub 1 over x sub 2 minus x sub 1, meaning that we needed 2 points on a curve to find the slope of, 2 points on a line to find the slope of that line. But the tangent line problem only gives us 1 point. And so algebra says you need 2 points. The calculus problem is we only have 1 point. So how do we fix this? And what we did, or what they did, I should say, I didn't have anything to do with this, is they used the idea of a secant line and turning a secant line into a tangent line. Now, just to review, in case you have forgotten or maybe never knew what a secant line was, a secant line is just a line that passes through 2 points on a curve. Right? And so what the calculus people did, what the early explorers of this type of mathematics did, is say, well, let's fix 1 point, that's the P, where we want the tangent line, and then we'll make up a second point over here, sometimes called Q, and the difference between these points is going to be a little bit on the x-axis, and that little bit on the x-axis we're going to call delta x, and then a corresponding little change on the y-axis that we're going to call delta y, and we are then going to say that the slope of the secant line would be that delta y, that change in y, divided by that delta x, that change in x. Now, if I were to make this delta x smaller, then this delta y would also become smaller. Or, if you like to see things in terms of a picture, if we were to take that second point Q and slowly move it along the curve, making it get closer and closer and closer to that point P, then the secant line, as Q got closer and closer and closer to P, would approach the tangent line, or that the slope of the secant line would become a better and better approximation for the slope of the tangent line. And if we could push point Q over here so close to point P that you couldn't tell them apart, when P became Q, the secant line would turn into the tangent line, or more importantly, the slope of the secant line would turn into the slope of the tangent line, and we would know our answer. We would know the thing that we're looking for. Right? So we need the slope of the tangent line. Algebra says you need 2 points. So we're going to make 2 points. And then we're going to find the slope of the secant line. And the way that we're going to find the slope of the secant line is we're going to say that the slope of the secant line is the y value at point Q minus the y value at point P divided by, now here's where things get tricky, because this denominator has been simplified. Originally the denominator was supposed to be this, x sub 2 minus x sub 1, right? And x sub 2 would be the x location of Q, which would be c plus delta x, c plus a little bit, it's right up here, right, minus x sub 1, which is the value c. But do you see what's going to happen with the 2 c's and how we're just going to get left with delta x? Okay. So this is the formula for the slope of the secant line. But what we want to do is we want to push point Q over to point P. And how do we do that? We take the limit as delta x approaches 0. Now, as delta x approaches 0, the slope of the secant line becomes the slope of the tangent line. Okay? Now, this is where last chapter comes into play, because if you attempt to do direct substitution, you're going to get this, right? Direct substitution would give me f of c plus 0 minus f of c divided by 0. These two cancel. We get 0 over 0, which I hope by now you recognize that 0 over 0 means somebody punched a hole in our graph. So the limit is going to exist. We're just going to have to do algebra to make it work. All right, so here's our definition that we're going to be working with for the big part of this chapter. And it reads, the definition of the slope of a tangent line to a curve says that if you have a function f and it is defined on some interval around the point C here represents the point that you care about. It's the point here. Let me get rid of all this extra gobbledygook. Okay? It's the point here, the one point that we care about, the point that we want to draw the tangent line at. It's the x coordinate of point P where we want the tangent line. Okay? And then you can find that slope provided that this limit exists. Now, there's only about one or two reasons why that limit would not exist. Okay, and we'll talk about those later. But for the vast majority of our problems, that limit is going to exist. It might take some work to figure it out, but that limit is going to exist. It's going to be some value, some numerical value, 5, -3, 2.8, something. And what's going to happen there is that limit is going to be the slope of our tangent line. And then once we know the slope of the tangent line, we just go back and use that point slope formula. Where these are the coordinates of our known point, and that's the slope of our tangent line. And so then this whole mess is going to be the equation of our tangent line. And here is something that I can tell you with a high degree of certainty. Finding the equation of a tangent line to a curve at a point will be on almost every exam for the rest of the semester. The equations will get uglier. Finding that slope might get more difficult, but that problem of finding the equation of a tangent line to a curve at a point will be on every exam for the rest of the semester in one way or another. Okay? Now, there are some reasons why this might fall apart on us. One is that if the tangent line were to be vertical at that point, that slope doesn't work because vertical tangent lines, vertical lines, no slope, that whole business. Now, if you're wondering what that looks like, I'm going to give you the one example that you might know. Because there's not too many equations that give you vertical tangent lines. Cube root of x, graph looks like this, comes in, wiggle woggles, go up like that, kind of, ish. Technically, right there at the point 0, the tangent line to this curve is vertical. And so if you attempted to use this definition on that curve at the point 0, 0, your limit wouldn't work. You would get a limit of infinity, essentially, because the tangent line there does not have a measurable slope. It's a vertical tangent line. Okay? And then if you're working with a function f on a closed interval, you can take this definition up here and figure out the endpoints by just using left-hand or right-hand limits appropriately. Okay? All right, so here's our first example. We need to find the equation of the tangent line to the curve y equals x squared at the point 1, 1. Right? Now I'm just going to copy down the definition. Definition said that m, the slope of the tangent line, I'm going to use this subscript to remind myself that I'm working with the tangent line, is going to be equal to the limit as delta x approaches 0 of f of c plus delta x minus f of c divided by delta x. Okay. Now over here to the right, I'm going to define what all these values are. What is c? What is f of c? Right? So c is the x coordinate of the point. F of c is the y coordinate of the point. Okay? So then I'm going to fill in or replace or do substitutions, however you want to think about that. So this becomes f of 1 plus delta x minus 1 over delta x. Okay? This is 1 because f of c is 1. This is 1 because c is 1. Then this becomes the limit as delta x approaches 0 of 1 plus delta x squared minus 1 divided by delta x. Okay? This is 1 plus delta x squared because the function is x squared. So I'm just taking the 1 plus delta x as the input into our function and squaring it. Now you should notice at this point, if you attempt to use direct substitution, so by direct substitution, you would get 0 divided by 0. Okay? So that means do more work. Okay, so I'm going to expand out that quadratic and see what happens. Okay, so then this is going to give me the limit as delta x approaches 0 of 1 plus 2 delta x plus delta x squared minus 1 divided by delta x. Okay? If I clean that up a little bit more, I get the limit as delta x approaches 0 of, the 1's cancel, I'll factor out a delta x. Right? So then what's this right here? Well, that's the hole in the graph. That's the piece that we ignore. So then this is the, if you go back to the definition, this is the g of x that behaves just like f of x. And if we then do direct substitution on that, we get 2. 2 plus 0 is 2. So what does that mean? Oh yeah. It means the slope of my tangent line is 2. And now I can use the point slope formula to find the equation of my tangent line. So y minus y sub 1 is equal to m times x minus x sub 1. I know that m is 2. I just found that. I know that x sub 1 is the x-coordinate of the point I care about. That's a 1. I know that y sub 1 is also a 1. It's the y-coordinate of the point that I care about. And so then putting this all together, I get y minus 1 is equal to 2 times x minus 1, or y equals 2x minus 1. The slope of the tangent line to the curve at the point 1, 1. Now, I don't trust myself yet, because this is the first one I've done, so I'm going to come over here to Desmos and see if this looks right. My original function was y equals x raised to the second. The point that I care about is the point 1, 1. And I think that the equation of the tangent line there is y equals 2x minus 1. How does that look? Well, I think that looks darn good. I feel pretty solid that that's correct. Looks like it's a tangent line to the curve at the point. Now, this graph does not prove anything. All this graph does is say, are you seeing what you think you should be seeing? I think I'm seeing what I should be seeing, so I feel good about this. All right? I found the equation of a tangent line to a curve at a point. All right? So just to review really quickly, tangent line problem. I want to be able to find the equation of a tangent line to a curve at a known point. Algebra fails me because algebra says you need 2 points, so I need something more powerful. The something more powerful is calculus. So what I'm going to do is I'm going to make a formula for a secant line slope, and then I'm going to take the limit as the secant line turns into the tangent line slope. Move the point Q over until it becomes point P. Okay? So I have a formula for that. I grind out a whole bunch of limit work here. I get a slope of a line. I use point slope, put it all together, and I get the equation of the tangent line to the curve at the point. All right? I'm going to end this video here because we're at 20 minutes. We'll come back and do a couple more examples in the next video.